Today we'll be talking about our magnetic force in a current carrying wire. And so yesterday we looked at what happened with moving charges in a field, but remember that current is just the movement of charge through a conducting material. We'll first start by looking in the lab and seeing, well, what happens when we have a current carrying wire in a magnetic field. We've already talked about charges moving through a magnetic field and the force that they experience. We showed that using our right-hand rule. Here we happen to have a magnet, a horseshoe magnet, and a wire passing through it. Now we can see the current going through that wire as it sits here. And by adjusting this knob, you can see I have my red connected to the positive end of my terminal, which then connects to positive end of my ammeter, and then back to the circuit with enough resistance. And we'll see what happens when we happen to have a charge or a current going through this wire. So just by adding a current, you can see that that increases. We notice that something strange starts to happen to my wire. This would be known as levitation. And we can see that as soon as I move it, it has no reason to stay up there without that current. But by applying a current through this, it has no want to stay down. As soon as I push it down, it comes right back up. This levitation can be shown using our right-hand rule. As you saw in the video, a magnetic force can actually get a wire to move all on its own by having a magnetic field. The reason for this is because there's a magnetic force being applied on the wire. By using our equation for a charged particle in a magnetic field, we can use our QVB sine of theta. And by using a little bit of knowledge that the current is Q divided by T, and that our velocity can be the length of wire that we have, divided by time, we can get a new equation for the force on a current carrying wire. And this comes out to be that the magnetic force is ILB times the sine of theta, where B is the strength of the magnetic field, I is the current, and L is the length. We can use this to do a problem like a voice coil of a speaker has a diameter of 0.0025 meters and has multiple turns. Basically, that means we're just going to multiply by 55 to whatever value we get. And it's placed inside a 0.1 Tesla magnetic field. The current in the voice coil is 2 amps. And we want to determine the magnetic force that acts on the coil and the cone. If you look here, you will see that we happen to have a magnetic field that goes from my north to my south poles on either end. The current carrying wire here is into the page, and therefore my force will be perpendicular. You have to use all three dimensions: north, south, east, west, and into, out of. Same thing on the bottom, but because of the fact we have these two different magnets, both of these forces are going to work together. Plugging this in, we use 2 times our 55 because there are multiples of this. The length of my wire just happens to be the circumference multiplied by 55, so that's pi times 0.0025, the diameter. And my magnetic field is 0.1, giving me a magnitude of the force of 0.86 newtons. As far as the force and using our right-hand rule, a few reminders. We're going to use our index finger to be our conventional current here. So the direction that our positive charges are flowing through our circuit, that's going to be what my I is. My thumb is still the magnetic force, and my B finger is the magnetic field. So still the same representation. With this application, we can start to see what happens to a loop of wire. And when you have a loop of wire, we can actually get some torques. And looking at torques, we're going to have to bring back our knowledge that torque is equal to R, the lever arm, multiplied by the force applied to the object, where that force is going to be our magnetic force we just talked about, times the sine of theta. When we look at a loop of wire in a magnetic field, then there are two parts of the wire that are going to experience a force. You have a current carrying wire that's coming out of the page, so your index finger comes up. My magnetic field is to the right, and so your thumb in that situation, although hard to kind of hold there, will be towards the north. And so that's what's shown here. For the other one, about my axis of rotation, so we're pivoting around this point. And so this object here, we're going now into the page with my current. My magnetic field is still to the right, and your thumb should be pointing south. And so both of these show the force. When you have a force that has at least a component perpendicular to my lever arm shown here, I will get a torque that happens. Both of these happen to be counterclockwise torques, and so they're going to add together to create the total torque of this system. And the nice thing about torques and current carrying coils is that the loop will rotate until the normal, or in other words, the face of that loop, becomes aligned with the magnetic field. That face can be shown as this area here. So when this face gets pointing along the same axis of the magnetic field, the forces that will be experienced will now be along my lever arm, and so the angle between my lever arm and my force is going to be 0 degrees. Sine of 0 cancels out, and so there's no torque in this system. And so an object that starts at a perpendicular position will experience a maximum torque until it gets to this position here where it has a minimum torque. We'll be starting to look at problems then that apply these torques on current carrying loops, and we're going to need some more equations to solve for that. More on that tomorrow, but be making sure you're able to use the equation that we came up with for our force, that F equals ILB sine of theta, as well as still using our right hand rule to determine the direction of the force on that current carrying wire. And now the levitation of a wire. Focus, focus. Ooh. That's the power of physics right there. Goes up and down. Up and down.